This video is about line integrals of vector fields as opposed to scalar functions. We'll motivate the definition of a line integral of a vector field by looking at the work done on an object moving in a force field, and then we'll talk about the 5 ways to represent a line integral of a vector field over a curve C. Now, here's the idea. Let's say you've got a particle moving along a curve given by R of t, piecewise smooth parameterization R of t, in 3-dimensional space. So as t increases, there's some particle and it's traveling along this path. At t equals a, it's over here, and t equals b, it's over here, and it's just going along this path in 3-dimensional space. Now, if there is simultaneously a force field here, so you've got little force vectors acting everywhere in the xy plane, or not xy plane, in 3-dimensional space. So F has components, let's say m, n, and p, because we're in 3 space. Well, then if you're an object traveling along this path, at each location on the path, you're going to experience a different force. Maybe the force is going that way, or the force is going that way, or the force is going that way. Who knows? And I should write here that the curve is given by a piecewise smooth parameterization R of t, where t goes from A to B. Well, if I want the work done on that object as it travels along this path in 3-dimensional space, the first thing I do is I subdivide our path into n little pieces. And so we just compute we find little pieces like this. And then we focus on one piece. You've got one piece at a time, and you find the work done on that piece. Well, the work done on that piece is the force, the approximate force, acting on our particle as it travels along that little piece, times the distance that little piece moves through. Now, I know you might be thinking to yourself, it's really a dot product of force with displacement, and you're absolutely right. But let's just say we're just going to use force and distance here, and that'll be fine for right now. Okay, so let's say that there's a force acting here, and I've made it larger for emphasis. And I want to know the work done on the object as it travels over this little piece. Well, the force acting on that object as it travels along this little piece is a force, the force given by this force field, evaluated at a particular x, y, z that's on that little subinterval. That force is going to be approximately constant when that interval is so small. But it's that force, but it's not the whole force. It's only the part of the force that's moving in the same, that is, parallel to the direction of movement. So we want the part of the force that's acting in the direction that the particle is going. So what we really need, if this is the unit tangent vector, is the projection of this force onto the unit tangent vector. So the magnitude of the force acting on this object as it moves over this little piece is the projection, or the magnitude of the projection of that force onto the unit tangent. But the magnitude of the force, or the projection of the force onto the unit tangent, is just the dot product of the force with the unit tangent divided by the length of the unit tangent, but the unit tangent's only 1 unit long, so we don't have to divide by it. times the distance that little piece moves through, or the distance that object moves through as it moves along this little piece. That distance is given by that delta S sub I. So if I want the work done by this force on this object as it travels along this curve, all I have to do is add up a bunch of pieces like this. So the total work done on the object is the line integral over C of F dotted with T hat ds. Now this does not always have to represent work. This is just one application, one example. This only gives us work when we've got some particle moving along a path given by r of t, and this is the t hat associated with that r of t, for t between A and B. And this F represents a force field. If it represents something else, that's not what this means. There are other applications, but this is one application that we use for this. Now this is one of 5 different ways that we can represent a line integral. It's really 4 different ways, but we're going to talk about one way in 2D and 3D, so that's going to give us 5 formulas. But this gives us work, because this is force acting in the direction of motion times the length that we're traveling, or the distance that we're traveling in the direction of motion. So we get this. But remember what t hat is. That's the unit tangent vector. We found that by taking the derivative of the position vector. So if we're thinking of that as if we're thinking of r of t as a position of some object, that's the velocity. And then we divided by speed. And then earlier, remember what we said about that ds. ds, as a tiny distance traveled by that object, is given by the speed times time. And since the speed here and the speed here will reduce, and of course that only happens provided that that speed is never 0, so the unit tangent is never 0. Then we end up with this. But r prime of t dt, that's the definition of dr. So this is another form of the line integral over C of a vector field F. Now there's also differential form. If we're in 3-dimensional space, F has components m, n, and p. And this dr, again, is r prime of t dt. If we're in 3-dimensional space, that's x. It's a vector with components x prime, y prime, and z prime. We're integrating with respect to t. So rather than writing the integral over C now, since I'm integrating with respect to t, I could let t run from A to B. Actually, I think I'll go back to C just temporarily because I want to show you the differential form. Now let's compute some dot products. We get m times x prime of t plus n times y prime of t plus p times z prime of t. Remember how we compute a dot product? We multiply and add, multiply and add, multiply and add, then multiply by dt. Well, if I distribute that dt to everything, end up with this. And the lack of parentheses bothers me, but this is standard notation. Most people don't put parentheses over everything. I'm gonna have to do it for myself. It's implied that that is a line integral over C of all of this that's in front of it, even if those parentheses aren't there. But remember, x prime of t dt, that's the definition of the differential of x, and the differential of y, and the differential of z. So this is called the differential form of the line integral over C. We've got m dx plus n dy plus p dz, where m, n, and p are the components of our field, and dx, dy, and dz our x prime of t dt, y prime of t dt, z prime of t dt. So we've got differential form in 3D, and if it was 2D, we would have that, but without the p times dz. Okay. So got the line integral over C of a vector field is this. And that's the same as this. And that's the same as this if we're in 3 space. Or the same as this if we're in 2D. Now in practice, you don't evaluate any of these. In practice, you evaluate integrals that look like this. So we need one variable to tie everything together. Remember our picture. If we're on a curve like this, and r is given by r of t, the variable that ties everything together is t. Because at this point, x, y, z, x is given by x of t, y is given by y of t, and z is given by z of t. So I can write r in terms of t using the parametric equations for that piecewise smooth parameterization of C. This field is usually a function of x, y, and z, and not t. So the force field doesn't depend on time. We don't have a different force at different times. We have different forces at different positions. But the force being experienced by the particle as it travels on this path is different at all of these locations. If I'm on this path and x is given by x of t, y is given by y of t, and z is given by z of t, it's as if that particle, well, it is, I want to say as if, it's not the right way to say it. The particle is experiencing this force as a function of time. So from the particle's perspective, this depends on time. So that force can be written in terms of t, because when we're on this path, x is given by x of t, y is given by y of t, and z is given by z of t. And so m, n, and p can be written in terms of t as well. So given all of that, the way I typically evaluate this is I look at it this way. dr is r prime of t dt, and I write my field in terms of x of t, y of t, and z of t. Now, if you're wondering, how can I take the integral over a curve of a vector? Well, it's possible to do that using the integration techniques that we talked about in our chapter over vector valued function. You just integrate component by component, but that's actually not what we have here. We don't have the integral over a curve of a vector. We have the integral over a curve of the dot product of a vector field, which is a vector, and another vector. So this dot product is going to yield a scalar function of t, and this is just a regular Calc 1 integral, nothing fancy. So these are all definitions. But this is the one we use. So those are our 5 equations for the line integral of a vector field f over a curve C. All of them mean the same thing. Now, of course, if we are in 2D, f is just going to depend on x and y, so there wouldn't be a z of t here. So then this would just be the dot product of a vector with 2 components and a vector with 2 components, as opposed to a vector with 3 components and a vector with 3 components. And 2 applications. If F represents a force field and C is a piecewise smooth plane curve or space curve, representing the path traveled by some object, from t equals a to t equals b. Then this line integral, that is giving me the component of force that's parallel to the direction of motion times the distance that we're moving in that direction of motion. And then we add them all up, and that gives us work. It's the work done by the force on the object as it travels along that path. Now, if F represents the velocity of some fluid, so I shouldn't have made that curve, but and maybe this is our curve C. And maybe it's more erratic than that. Maybe sometimes it's going over here and here. Who knows? So got this field F. And we still have our piecewise smooth curve C. If that's the case, if I take the dot product of this velocity with the unit tangent vector, so this is the water, or this is the direction that that fluid is moving at that particular location. And then I take the dot product of that with the unit tangent. So that's giving me the projection of that velocity that is in line with the curve. If I take that and I multiply by that tiny distance that it's acting over, and then I add all of those up, that's called the flow. I want to say flow of F, but maybe it's flow of the fluid. I have to look that up again. Over the curve C. And it's this. But it's basically a measure of how much that fluid is moving along C, sort of with C, as opposed to crossing C. We're going to talk about the flux of the field over C in another video. So this can either represent work or it can represent fluid flow. If the curve C happens to be closed, we call that the circulation. If this curve C is closed and F is the velocity field of some fluid. And I'm not sure about this of F, so maybe I should put a question mark around that. Like flow of the fluid, flow of F, I'm not sure. And that's just a notation meaning to tell us that the curve is closed. That closed curve just starts and ends at the same place. Okay, so let's actually evaluate one of these integrals. I'm just going to do one because I think the principle is exactly the same. Just remember, if we're in 3D, it looks like this. If we're in 2D, it looks like that. You could also always rewrite it this way or this way. You just have to remember to write m, n, and p in terms of t, and dx as x prime of t dt, dy as y prime of t dt, and dz as z prime of t dt. But that's equivalent to this. So let's do an example. We'll just do a 2D example. So let's say you've got a force. Well, let's say we have an object, sorry, traveling along the path given by y equals x cubed. From a certain point on that path, let's say 1, 1, to the point 2, 8. So we've got an object traveling along the path and a force field given by this very simple force. It's just x times I hat plus 2y times j hat. Or in component form, we can write it this way. Say somebody asks you to find the work done by the force on the object. Well, we're going to start this problem the same way that we start pretty much all of the problems involving line integrals. We've got to find a piecewise smooth parameterization of this path. Or in other words, you need to find r of t. So I'll sketch it. Y equals x cubed looks like this. But we don't get the whole curve y equals x cubed. We start at the point 1, 1, and we end at the point 2, 8. So we're just talking about this part of that curve, and the direction matters here. If we're traveling along this curve this way, the unit tangent points that way. If I'm going from this side to this side, the unit tangent points in the opposite direction. Multiplying that angle, or adding pi to each of those angles, multiplies this dot product by -1. It would give us the opposite answer from the answer that we're looking for. So remember, the orientation matters. If they tell you you're starting at 1, 1 and ending up at 2, 8, you have to define a parameterization that goes from here to here, not from there to there. But since we're on the curve y equals x cubed, that's pretty simple. Let's just let x equal t. Since x goes from 1 to 2, let's let t go from 1 to 2. Easy breezy. And if x is t and y is equal to x cubed, well, I just replace x with t and I get y equals t cubed. So now I've got my piecewise smooth parameterization. And if I want to evaluate this line integral here, what I need is the field in terms of t. I need r prime of t. I need to compute a dot product, and then I need to integrate over the interval of t values, which we just stated. T went from 1 to 2, so that's my a and that's my b. Okay, so let's set up the integral and then find all of the pieces that we need to finish setting up the integral, and then we'll substitute and then we'll evaluate the integral. Okay, so the work will be the integral from a to b of f, written in terms of x of t and y of t. Started writing it as if we were in 3D, but we're just in 2D. And we're going to dot that with r prime of t dt. And that's it. So the first thing I need when I look at this integral, I see I need my field in terms of t. This is not too bad at all. The field f is pretty simple. It was just x times I hat plus 2y times j hat. X is t, y is t cubed. So I've got 2 times my y value, which is t cubed. So remember, you're just replacing x with x of t and y with y of t. So x has been replaced by t and y has been replaced by t cubed. That's my field. Now I need r prime, and then I need to take a dot product. This is very, very simple. I know it's not simple when you're first learning it. I don't mean to minimize what you're doing at all. Multivariable calculus is tough. But once you get it, it's just a very simple process. Yes, that's how everything is though, right? Everything is easy once you get it. So we've got r of t, now we need to compute r prime. Derivative of t is 1, derivative of t cubed is 3t squared. Okay, and now we want to compute the dot product. We want that field dotted with r prime, where the field has been written in terms of t. So we had t and 2t cubed, that's our field in terms of t, and we're dotting that with 1 and 3t squared. Remember how dot products work? You multiply and add. So we have t times 1 is t, and then we add 2t cubed times 3t squared. 2 times 3 is 6. Add the exponents, that's t to the 5th. That's our integrand. And we'll substitute into the integral and evaluate. So our work is the integral from a to b of f dotted with r prime dt. But of course, this is a function of t, this is a function of t. And t goes from 1 to 2. We're integrating t plus 6t to the 5th dt. Very simple Calc 1 integral. Add 1 to the exponent, divide by the new exponent, bring the 6 down. Add 1 to the exponent, divide by the new exponent. Substitute in 1 and 2 and subtract. So we've got 1/2 of 2 squared plus 2 to the 6th minus 1/2 plus 1. So we've got 2 plus 2 to the 6th. That's 64. Yeah, that's 2 times 2 times 2 times 2 times 2 times 2, 8 times 8, 64. 64 plus 2 is 66 minus 1.5. So it's that 64.5. That's the work. I know it needs units. It really depends on the units for the force and that dr though. So I need to know what are my units of distance and what units am I using for force. Multiply those together and that's going to be the units for work. Okay. Now I want to show you what the same integral would look like in differential form. So someone might say, evaluate this integral. And the integral is a line integral over c of x dx plus 2y dy. That is going to give us 64.5 again, because m and n are the components of f. That means F is the field with components X and 2Y. It's the same field that we looked at in the last problem. Now, when we came up with that piecewise smooth parameterization for C, which happened to be a smooth parameterization, we're on something that looks like this. This implies that X of T, that's our X component, that's T, and Y of T is the Y component, that's T cubed. And we also had bounds. We started at 1, 1 and ended up at 2, 8, so T goes from 1 to 8. If I want to use this differential form, I need to compute dx and dy in terms of t. So dt, or dx, is the derivative of x, which is 1 times dt. dy is the derivative of t cubed, which is 3t squared times dt. Now, if I want to evaluate this using this method, I just substitute. I replace x with x of t. I replace y with y of t. I replace dx with 1 dt. I replace dy with 3t squared dt. And we use these bounds. So this integral up here is the integral from 1 to 2 of x, which is t, times dx, which is dt, plus 2y, so that's 2t cubed, times dy, which is 3t squared dt. And if I factor out the dt, you see we get exactly the same integral here that we got here. We still have a t to the first plus 6t to the fifth. The result of this dot product is that, and that's exactly the same as the result of this. The only difference is this one already has the dt distributed, and we actually have to pull it out before we integrate. I prefer this form personally, but if I see something like this, I've got two options. I can either evaluate it this way by calculating dx and dy in terms of t, substituting and integrating, or I can say, my field is x times I hat plus 2y times j hat, and then go up here and do this. This is my preference. I think that this dot product notation is really compact and really easy to work with. But that's how we evaluate that other notation. That's called differential form of the line integral. Okay, so here are our 5 forms, the 5 forms that I told you, that I promised you we'd talk about. And I need to throw away that highlighter. Whoops. There we go. All right. So this is the definition. This is finding the part of that field that aligns with the unit tangent vector along your curve. So if you're tracing out your curve in this direction, you're gonna get one answer. If you trace out this same set of points, you go along the same path, but in the opposite direction, you're gonna get a negative, the negative of the value of this one. So if I call this one C1 and this one C2, it's a fact that the line integral over C1 of this dot product is equal to the negative of the line integral over C2 of that one. And that's because I'm basically taking my unit tangent and I'm flipping it. I'm changing its direction. And by changing its direction, that's going to change the signs of all of those dot products. Okay, so I find the part of my field that's aligned with the unit tangent, and then I multiply it by a tiny distance that I'm traveling along the path. And I do that a bunch of times, and that gives me this line integral of f along C. That can also be rewritten this way. And this is really just f dotted with dr, which is r prime of t dt. Now here's the differential form of the line integral in 3D and in 2D, but this tends to be the one we use. That's what it looks like in 3D. In 2D, it looks exactly the same, but without the z of t. And of course, we've got two applications. If F is a force, this represents work. If F is the velocity field of a fluid, this represents flow. If that curve is closed, we call it circulation. I think that's it.